In this video, we're going to talk about joint continuous random variables. Now, this stuff is new. You've seen continuous random variables and you've seen joint discrete random variables, but now we're going to combine those two ideas. And I want you to notice in this video how much stays the same. Basically, the only thing that changes is that sums become integrals, and so double sums become double integrals, and that can be a little bit scary, especially if you're not super great at calculus like myself. But we promise we're going to have relatively straightforward integrals, and a lot of the probability related stuff stays exactly the same. So we want to start off with the definition of the joint probability density function. And so if we have a bunch of continuous random variables, x1 through xk, the joint PDF is this little f of x1 through xk, which is the derivative of the joint CDF. And we take the derivative once with respect to each of the arguments. So that little symbol there is a die. We just take k partial derivatives, one with respect to each of the xi's. And that is defined for all places where that derivative exists. So all k tuples x1 through xk, where the derivatives exist of big F in the joint support of those random variables x1 through xk. So there might be points of non-differentiability, and that's all right. So if we have two continuous random variables with a joint PDF little f of xy, we can find the marginal probability density function of x by just integrating over all y our joint PDF. And same thing in the other direction. We can get the marginal PDF of y by integrating over all x. So the principle is actually the same. We're just integrating over the unwanted random variables. We can say that x and y are independent. Again, this definition is very similar to the discrete case if the joint probability density function is the product of the marginals for all pairs xy in the joint range. There's some neat things that we can do to check for dependence or independence in the continuous case. As before, if we have the joint range or the support of the two random variables being something other than a rectangle, then we definitely know that we have dependence between the two random variables. If it's, say, the entire xy plane, that's fine, but if it's anything other than a rectangle, that's no good. But if the support is a rectangle, and we can factor f of xy into some function of x times some function of y, then they are independent. That's kind of different from the discrete case. In the discrete case, it's tricky to prove independence. You would have to check every single possible combination of x and y. But in the continuous case, we have a little trick. If we have a rectangular support, so a Cartesian product of sets, and we can factor f of xy into g of x times h of y, then we know that they're independent. But we have to have both of those things. If we only have one of them, that's not enough. We need both of those to prove independence. And that's actually easier to check for in the continuous case. I want to look at an example, and we're going to come back to this example several times over this video. So suppose x and y have a joint PDF given by f of xy equals cx squared for 0 less than x less than y less than 2. Now right away, we can tell here that these two variables are not going to be independent because we know that x must be less than y. So that means the ranges of the two variables depend on each other, and so they can't possibly be independent. What I want to do in this situation is find the value of c that makes this a valid joint PDF, as well as the marginal PDFs of x and y. Now, the first step in any joint continuous question is always to graph the support. Everything is easier if you have a graph of what the values look like. So here we have the xy plane, x and y, and I've put 0 and 2 there on both axes, and we know that x is less than y, which is less than 2. So it's going to be, I've drawn the line there, x equals y, and think about whether it's going to be the upper part or the lower part of the triangle that corresponds. It will be the upper part of the triangle. Now that seems kind of weird. You think x is less than y, shouldn't it be the lower triangle? Well, just pick your favorite value of x. Pick x equals 0.5. That means that y has to be greater than 0.5. So any point that you think of will end up in that upper triangle, not the lower triangle. So once we have the support, that's the very most important first step, then we can proceed with the other stuff. In order for this to be a valid probability density function, we want to find the value of c such that the integral over the entire range of f of xy is equal to 1. And we could do this integration in either order. So we could start by integrating with respect to x, and then that's obviously going to go from 0 to 2. And then for each value of x, we can kind of carve it up like that. Y goes from x up to 2. So the integral would look like this. The integral from 0 to 2 dx and the integral from x to 2 dy of f of xy. So we could do it that way. Or, remember, we could integrate in the other order. So we could let y go from 0 to 2, so we're integrating with respect to y. And then if we carve it up that way, x is going to go from 0 up to y, and then we have this integral here. So both of those integrals are exactly the same thing. They're the double integral over that triangle of that function f of xy, but we could do the integration in either order. And we're actually going to use the second way because it looks a little bit easier. Having zeros for the endpoints of those integrals makes it a little bit easier to work with. So essentially we want to take that second integral and set it equal to 1 and then solve for c. So we'll do that. We'll have our integral here, and then we're going to evaluate the inside integral there. And remember, it's with respect to x, so that will give us c x cubed over 3, evaluated at 0 and y. And then when we have that, that's just c over 3y cubed that we're integrating from 0 to 2. So that will be c over 12 y to the 4th, evaluated at 0 and 2, which is going to be 16c over 12. And we need that to equal 1, so the only possible value of c is 3/4. Then we can find the marginal probability functions, and they're going to be fx of x is the integral over all y of f of xy dy. So now for any particular value of x, we know that y can go from x up to 2. So we're going to integrate 3/4 x squared dy from x to 2. So we'll evaluate that integral, and we'll get 3/4 times 2x squared minus x cubed for 0 less than x less than 2. Notice here, nothing in this expression involves y, and it can't, right? This is the marginal PDF of x, so y cannot appear anywhere in the range or in the function itself. We've taken away all the information about y when we did that integration. So it's just 3/4 times 2x squared minus x cubed for 0 less than x less than 2. Similarly, we can go in the opposite direction. We'll have fy of y as the integral over all x of our joint PDF. So that's the integral from 0 to y of 3/4 x squared dx, which is 1/4 x cubed evaluated at 0 and y, which is just y cubed over 4. And again, for 0 less than y less than 2. Again, here we have no x appearing anywhere in the expression or the range because this is just information about the variable y after we've removed all the information about x. I want to note a couple of things. First of all, for some values of x or y, these functions, little f of xy, little f sub x of x, or little f sub y of y, could be bigger than 1, and that's okay for PDFs. And also, we could, if we wanted to, find the marginal CDFs. So for example, we could take the integral from 0 up to y of u cubed over 4 du, that's our PDF of y, and that would give us our CDF of y, which is y to the 4th over 16. And that holds between y is between 0 and 2. So you could check if you want that this is a valid CDF, it's continuous, it is non-decreasing, and it starts at 0 and it ends up at 1. And give it a try for x as well. See if you can find the marginal CDF of x and check that it's a valid CDF, that it's non-decreasing and continuous. We can also find the probability of any statement we like that involves the random variables x and y by just integrating our joint probability density function over the region in the xy plane that satisfies that statement. So I want to give you an example. Let's look at that same problem before, but now we want the probability that x plus y is less than 2. Well, if we draw our support here, we know that the range of the two random variables is that upper triangle, and if we want x plus y to be less than 2, we actually know that that's going to fall into that shaded region there, that triangle. So again, we're going to integrate over that shaded region f of xy with respect to both variables. Now, again, we could do this in two different ways. If we integrate with respect to x first, x goes from 0 to 1. And then for each value of x, if we slice it up this way, y is actually going from x up to 2 minus x. So we could integrate our joint PDF in that direction. But we could also do it the other way. We could integrate with respect to y first, but notice that it's going to be a different function from y going from 0 to 1 and y going from 1 to 2. So we have two different integrals we want to split this up into. For the first part, then x is going to go from 0 up to y, so we'll integrate there. And for the second part, x is going to go from 0 up to 2 minus y, so we can integrate like that. So again, this is two equally good ways to split up and define the integral of the function f of xy over this shaded region. Give it a try and see if you can get 1/8, and it should be the same either way. In terms of expectation and covariance, in the joint continuous case, actually everything is basically the same as it was before. So e of g of x is now just going to be a double integral instead of a double sum of g of xy times f of xy dy dx, or of course we could do that integration in the other order. So it doesn't matter if we integrate with respect to x first or y first. Sometimes one way is easier than the other, sometimes it doesn't really make much difference. But basically it's the same thing. Linearity of expectation still holds, and the proof is identical, you just have integrals instead of sums. And as well, if x and y are independent, then e of some function of x times some function of y is the product of those expectations. Again, the proof is identical to before. The definitions of covariance and correlation are exactly the same as they were before, and the interpretation of covariance and correlation are also exactly the same as before. So everything basically stays the same in terms of the relationships between variables. The only thing that's different is we have integrals instead of sums. All right, let's look back at our example. We had little f of xy is 3/4 x squared for 0 less than x less than y less than 2, and we're going to find a few things. First of all, we want the means and variances of x and y on their own. Second, we want e of xy, that function of x and y. And lastly, we'll find the covariance and the correlation and see if we can justify why the sign of those quantities makes sense. For this one, I am going to walk you through the integrals in a bit more detail than I did for the example in the previous video, but not all of them. So make sure you follow along and see if you can do those integrals yourself. Let's get started. So for A, we already found the marginal PDFs of x and y. So we can just use those to find the means and variances. So for x, we had this marginal PDF, and thus the expected value is the integral over all x, which is from 0 to 2, of x, f of x dx. All right, well, we can evaluate that. That's going to be 3/2 x to the 4th over 4, evaluated at 0 and 2, and 3/4 x to the 5th over 5, evaluated at 0 and 2, which should get you 1.2. Similarly, e of x squared will have the integral of x squared f of x dx over all x. And again, plugging in using this nice integration of a polynomial here, we end up with a value of 1.6. And if we combine those together, that gives us that the variance of x is 0.16. Similarly, we know that f sub y of y was y cubed over 4 for y between 0 and 2. And so again, we can find the expected value and the variance are 1.6 and 0.106666 repeated respectively. So do give that a try. Make sure you can find that. That's a fairly straightforward integration, so I didn't feel like I needed to show you all the details. For part B, we want the expected value of xy. So again, by definition, this is the integral over all x and all y of that function, xy, times the probability density function, dx and dy, or dy and dx. It doesn't matter the order in which we go in. And actually, we could do it in either direction, just like before when we were finding the constant that made it a valid probability density function. We can integrate with respect to y first and then x, or x first and then y. But as before, the one that was a little bit easier to work with was the one where y was on the outside and x was on the inside, because then two of our endpoints of our integrals were 0. So let's do it that way. You can check the other way if you really want to. So we'll integrate with respect to y from 0 to 2, and then with respect to x from 0 to y of xy 3/4 x squared. So our inside here, integrating with respect to x, we get 3/4 y x to the 4th over 4 evaluated at 0 and y. And notice here, inside this integral, when we're doing that interior integral, y is just a constant. So we end up with this result here. And then when we evaluate that at 0 and y, that just gives us 3/16 y to the 5th dy. Well, then we can integrate that. That's just 3/16 y to the 6th over 6. And then we evaluate that at 0 and 2, and we should get 2. Double check that. So then finally for part C, we can find the covariance. It's going to be e of xy minus e of x times e of y, which is 0.08. And the correlation is our covariance that we just calculated divided by the square root of the two variances. When we put that in, we get 0.612. And I want you to think about what these values mean. So we have a positive covariance and a correlation that's fairly strong. And why does that make sense in this situation? So think about that for a second. If you remember what the graph of the support looked like, we had it as an upper triangle. So we know that this covariance can't possibly be 0 because there's clearly some kind of linear relationship going on. And the other thing to notice is that x, by definition of this random variable, is always going to be less than y. So the bigger x is, that forces y to be even bigger. And that tells us that they tend to move in the same direction. I mean, of course, we could have some cases where x is small and y is large. But if x is big, y must be even bigger. So there's definitely a positive relationship between these two variables. And the strength of the relationship is pretty strong. 0.612 is a fairly strong positive correlation because one variable is literally forced by the range to be bigger than the other one. So hopefully that makes some sense why those values are positive. The last thing I want to look at in this video is very, very briefly the idea of a multivariate normal random variable. So I want to start informally. Imagine we have a plane, and it's kind of hard to draw in 3 dimensions, but I'm going to give it a try. So there's x1 and there's x2, and there's f of x1, x2. The multivariate normal distribution kind of looks like this. So no matter whether you're looking in one axis or the other, we have a nice little normal bell curve. And essentially it kind of looks like a sheet of like fondant when you're making a cake that someone has pushed up their finger underneath. We end up with this kind of surface of this function, little f of x1, x2. So that's the 2-variate case, but we can actually extend it to as many variables as we like. And each one of the variables, if we look kind of at a cross section of this function, is going to look like a beautiful normal bell curve. So imagine we have a bunch of random variables, more formally now, x1 through xk, that are each normal with their own mean mu I and their own variance sigma squared I. So each variable is normal. And we're going to allow these to have some dependence if we want them to. So the covariance of each pair will give the name sigma ij. And we're going to just define for convenience mu to be a vector of those means, and sigma, that's a capital sigma, to be the matrix of the variances down the diagonals and the covariances on the off diagonals. So this is sometimes called the variance covariance matrix, or just the covariance matrix, but essentially we're just taking all of the variances and covariances and piling them into a matrix to keep them all as one object. Interestingly, if we had independent random variables, then all of those covariances would be 0, and we'd end up with a diagonal matrix. So that's kind of neat. But in general, we're allowing there to be some non-zero covariance in any or all of those pairs. So if we have this vector mu and this matrix sigma, we say x1 through xk follows a multivariate normal distribution with this mean vector and this covariance matrix as our MVN for short, as multivariate normal. Some cool stuff is going to happen with them. In particular, any linear combination of those xi's is also going to turn out to be a normal random variable, which is pretty neat. So imagine we have some linear combination, ai xi, as I goes from 1 to k, then y is a normal random variable itself. And its mean and variance can be calculated using the rules for means and variances of any linear combination. So the mean is just going to be the sum of ai times mu I, and the variance is going to be the sum of ai squared times the variances plus 2 times the sum where I is less than j of ai aj times the covariance of xi and xj. So the mean and the variance of that linear combination we knew already from last time. But what's new is the fact that this combination is going to be a normal random variable as well. So no matter what the relationship is between these variables, whether they're independent or whether they do have some covariance, if the distribution of x1 through xk is multivariate normal, then any linear combination will also be a normal random variable, which is pretty neat. We're going to not see much of this until we talk about Brownian motion, but I wanted to introduce the idea now. So that is everything for this video and everything for this week. I will see you in the tutorial on Wednesday where we'll get some time to play around with the multinomial distribution. See you then. Bye.